Alrighty, welcome back to the C++ course. This is chapter 9, and it's a little bit of an odd duck, I suppose, in the sequence of topics that we're going through this semester. Most of the chapters so far have been the familiar suspects, variables, basics of computer memory, loops, if statements, the familiar suspects in any introductory computer programming course. This chapter is a bit different, like I said. This is all about searching, sorting, and algorithm analysis. And really, the first two topics, searching and sorting, are contexts in which we can talk about the third point, algorithm analysis. When you talk algorithm analysis, you really need to talk about them in concrete terms. And searching and sorting are some of the easier ways to talk about this thing called algorithm analysis. And it is a little bit strange to include a lesson like this in a two-year college's computer programming courses. In other words, this is something you see more in like four-year computer science courses. In a computer science course that I took, we talked almost exclusively about algorithm analysis. So it is a big topic. This is just sort of scratching the surface, but it is, in my opinion, one of the most interesting topics in all of computer science because it introduces the science piece to computer science. What we've been doing so far really has been computer programming. There hasn't been really much science, and algorithm analysis introduces some scientific terms and scientific ways to sort of analyze our code and see how it would perform with inputs of different size. I will say that there's not as many hands-ons in this chapter. It's going to be a bit of a shorter lesson, I'm sure. This one in particular, it'll be important that you, seems like I say this for every chapter, go through and read the material. When I encountered this for the first time in university, I found it very strange and foreign to me. I'd had a lot of computer programming experience before I got to university, but I'd never encountered anything like this. And the more I sat and chewed on it, the more interesting it became and the more interested I became in it. So I just encourage you, if this seems a little bit out of the ordinary, stick with it, especially if you're thinking about transferring to a four-year college. This stuff shows up all the time in almost every class that you would take, any computer science class at a four-year college. So let this be your gentle introduction to the topic. All right, so we're going to talk about some problem contexts before we get into the meat and potatoes of the chapter. So introduction to searching algorithms, searching through an array of objects to see if an array contains a given element. Introduction to sorting. So just like searching an array, we are going to sort the array to see if it can be sorted from ascending to descending or vice versa. We're going to look at vectors, how to sort and search them. And then, like I've been saying, an introduction to the analysis of algorithms. I will say in that point 9.6, there's additional supplemental material that I'll be pointing out for both the college course and the YouTube course. And I'll be showing each of you how to get a hold of that supplemental stuff. Okay, an introduction to search algorithms. So what does it mean to search? So it means to locate a specific item in a list. And that's a very generic term, list. And we can basically talk about arrays or vectors or anything that's kind of a sequential ordering of data when we talk about search. And there are tons of ways to search through lists of data to try to find a piece of data that you're looking for. When I say tons, I'm not really exaggerating that much. There's probably hundreds, if not thousands, of ways to search through a list of data. And we're just going to talk about two here, linear search, sometimes called sequential search, and then binary search. And both of these, if you yourself have ever had a situation in real life where you're needing to search through a list of stuff to find something, they're very natural sort of human algorithms to do this. So it's just a matter really of taking what we know intuitively as humans, translating that into something that a computer would be able to understand. So once you understand like the human part of this, translating it into programming code is going to be our main challenge. So linear search, what does that look like? If we have a list of data, this is pseudocode by the way, we're going to set some found Boolean variable to false. So we're going to assume that the item that we're looking for has not been found. We're going to set our position in the list to -1. So basically, we're going to set the index to 0. So we're starting at the beginning of the array. And then we're just going to say, again, this is very, very a natural way to think about searching. We're just going to say, well, index is less than the number of typos, elements, and found is false. So we're just going to go element by element through this list. And while our index is less than the number of elements, this is just like in our for loop when we're iterating through a for loop, iterating through an array in a for loop. We're just looking at each element of the array. So while the index is less than the size of the array and we haven't found what we're looking for yet. While that is true, so two conditions combined with the and, if our array at position index is equal to the search value, whatever we're searching for, we're going to set found equal to true, and then we're going to record what position it was found at. That's why we set the position variable up here to -1. That means that we haven't found what we're looking for yet. Also, the Boolean found set to false. That means we haven't found what we're looking for. But once we do, we're going to set that found Boolean to true and record the index at which the searched for element was found. So that's the end of that if, and then we add 1 to our index, so we're going to keep looping. But then say we found our element that we're looking for. Now, this condition is not true anymore. So our index may still be less than the number of elements, but found is now true. So we'll end that while loop. Then we'll return position. So at the end of this little pseudocode snippet here, basically the position variable is either going to be equal to -1, and I'll ask you, what does it mean if when we get out of this algorithm, what does it mean if our position is set to -1? Well, it means we haven't been able to find what we're looking for in the list. So if we get through that and it's -1, the item we're searching for is not in the list. If it's any other index, that means we have found what we're looking for and we're just returning where it was found. Needless to say, this simple algorithm would not handle the case where what we're looking for exists multiple times in the list. So this is going to find the first occurrence of a given value and return what that is. There's ways to basically handle the situation where you have multiple occurrences. This is not it. Because when we find it for the first time, we're ending the while loop and returning out of the function or the algorithm. Okay, concrete example here. So it's an array called numList. Here's a sample array, 17, 23, 5, 11, 2, 29, and 3. And if we're searching for the value 11, and we're using linear search to do so, we start at the beginning of the array. 17 is not equal to 11. 23 is not equal to 11. 5 is not equal to 11, but hey, 11 is, and so we return the position at which it was found. So it would return 0, 1, 2, 3. It would return the integer 3. Another example, so 7, we're looking through all of our array elements. 7 never appears, so our return value would be -1. As a little preview for what we're talking about near the end of the chapter, I would ask you to consider what is the worst case scenario. Obviously, the worst case scenario is we don't find it at all. So I guess what is the second to worst case scenario? What is the longest amount of time this thing would take to run? If we have 6, 7 elements here, and we're searching for the number 3, that means we have to search every single array element until we found what we're looking for. When we talk about analyzing algorithms like this, we oftentimes talk about the worst case scenario. And in this case, if we didn't find it at all, that would be a worst case scenario. But also, if the thing we're looking for is at the very end of our list, that would be another worst case. Best case, obviously, is 17. It's the first item in the list. But worst case, it would be 3, where the item we're looking for is at the very end of the array or the list. Benefits and drawbacks. There are always benefits and drawbacks to life and in computer algorithms. So the benefit is it's obviously very easy to understand and to implement, and the array elements can be in any order. There's no particular order to the items in this array. They're just kind of randomly put in there. Disadvantage, so it's inefficient. In other words, it's slow. It basically examines the number of elements divided by 2 on average for a value that's found in the array, and then n elements for a value that's not in the array. So on average, the average search time here, I guess, would be half of the array elements. Worst case, it's going to be n elements, or the number of elements in the array. And then best case, it's going to be the first element. Let's take a look at this on page 614, see if we can implement it. This is chapter 9. Oops. Project name EX9-1. I wish they would put the solution name first. Solution name chapter 9. Very good. Oh dear, I have my Steam open. Let me close that for you. Somehow. Oh man, you can see my Steam. There we go. Okay, we've got our standard namespace included there. For some of these algorithms that we're going to be using, sometimes we have to include extra libraries, sometimes we don't. Since we're implementing our own linear search here, we don't. And I will say that the STL, if I can type today, the STL that we talked about last time, the standard template library, does contain very fast, efficient implementations of everything we're going to talk about. So there is kind of a standard way to do searching. There's a best way to do it in C++ and in virtually any programming language. And the STL gives us access to that best way. So I know it seems like we're sort of reinventing the wheel here, trying to come up with really interesting ways to search through a list efficiently. But that's really just for learning purposes. Again, there are definitely better ways to search than the two that we're going to look at today. But again, it's just for demonstration purposes. So let's prototype our function. Let's say int linear search is going to accept a const int array. So that means that we're not going to be modifying the array in the function, and then 2 integers. Let us implement that function. So int linear search accepts an const int array, int size, int value. So value is the thing that we're looking for, basically. Sometimes called a needle. So needle in a haystack is the analogy that's sometimes used. Our haystack is the array, basically, and our needle is the value that we're searching for. So we have an int index equals 0, int position, just like in the pseudocode, equal to -1. Bool found equals false. So while index is less than the size of the array, and found is equal to false. If you look in the book, they have and not found. That is the same as what we're saying here. I used to be all about this like not found syntax, but I find that found equals false is more verbose. And especially in an introductory programming course, I think we can just be very explicit about what our conditions are here. So if array at our index is equal to value, we're going to set found equal to true. We found what we're looking for. We'll say position is equal to index. Regardless, we'll say index plus plus. The loop will iterate again. Then when we're done iterating, when we've either found what we're looking for or we've reached the end of the array, we'll return position. Back up in main, create a const int size equals 5. Int tests of size 5. I'll use my own data here. Yep, that's 5 elements. Int result. Result equals linear search, searching the tests array of given size for the value, in this case 100. If result is equal to negative 1, didn't find it, else you found it. And that's basically going to print out a human readable result of where it was found. So instead of displaying the zero-based index version of where we found it, we're just going to add 1 to it. Result plus 1. Is that a typo? Results. They have results here in their sample code. I think that is a typo. Yes, should be singular result. All right, let's fire it up. There's no input, so we just hard-coded everything. So of course we didn't find it. We're looking for 100, and it doesn't exist here. How about if we look for 5? There it is at location 5, and of course we need some spacing, but we did find it at index 0. Well, yes, index 0, 1, 2, 3, 4, plus 1. It's in the 5th spot, basically, for non-programmers. That would make a little more sense for them. Very good. Simple searching algorithm. Binary search. Okay, so we've also probably done a binary search. When I went and tested your projects from a little while ago, you had a guess the number project, where you basically said, hey, user, guess the number. I've randomly generated a number behind the scenes. Now you guess what it is. And almost always I would say, is it 50? No. Is it higher or lower? Higher. Okay. Is it 75? No. Higher or lower? Lower. Okay. Is it 65? And I just kind of have it each time until I found the number. And that tends to be the most efficient way to find it, at least in your simple guessing games. But that's exactly what we're doing. We're looking at the middle value in the array. And oh, by the way, the array must be in order, either ascending or descending order, but all the elements in the array must be in order. That is a critical presupposition to this algorithm. So if the middle element has the desired value, you're done. If I guess 50, you say guess the value between 0 and 100, and I guess 50, and that's it. Hooray, I'm done. Otherwise, see which half of the array may have the desired value. Continue working with this portion of the array. Repeat steps 1 and 2 until the element is found or there are no more elements to examine. So it may be the case that I don't find what I'm looking for, in which case we'll probably return -1 or something. Here we have numList2. So this is an in-order array, ascending from 2 to 29. We're looking for the number 11. So we basically cut the array in half, and it turns out that the middle element of the array is 11. We found it, so we stop. If we're looking for the number 7, first of all, we start with 11. We see that 11 is more than 7, so we're going to search this half of the array, divide that in half, see that the midpoint between that half of the array is 3. We know that 7 is greater than 3, so this is the only element left, number 5, which is not 7, so we return that this is not found. Benefits and drawbacks. So it's much more efficient. For an array of n elements, the number of comparisons is the smallest integer x such that 2 to the x is greater than n. When n is 20,000, for example, x is 15. If you think about it, we're really only searching that many elements. We don't need to, like with linear search, we don't have to examine every single element of the array. If this thing was 1 million elements long, no way. We would not need to look at all 1 million elements like we would potentially have to with linear search. We're dividing in half each time and examining which half of that division contains, possibly contains the number that we're looking for. Big caveat, of course, requires that the array elements be in order. 618. and I think we'll just talk through this one. That does seem like a big caveat that your array must be in order, but if you're keeping track of things like player scores or something, when you add a new player score to your player scores array, when you're keeping track of that array, when you're managing it, when you're adding items to it and removing items from it, you can be smart about how you insert items into that array. You can make sure that when you're adding items to it, that the order is maintained. So just a thought there. I guess what I'm trying to say is a little work up front is going to make it much more efficient for you to search it later on. All right, here's our function prototype for binary search. Accepts an array of ints, probably the size and then the thing that you're looking for. Okay, down here is the implementation. So in the binary search function, we have several integers. First is equal to 0. Last is equal to size -1. Then we have the middle position, and then our current position of the found element, which again is defaulted to -1. So while we haven't found what we're looking for, and the first is less than or equal to the last, do stuff. Let's see if there's a good graphic in here of this. Not really, is there? We can still talk through it. Okay. So we're going to find, so we assume we've just entered this for the first time. We're looking at the entire array. So what we're going to do is find the midpoint. We're going to say middle equals first position plus last position divided by 2. So when this is run for the first time, first is 0 and last is equal to basically the size of the array. Divided by 2. That's going to give us our middle index. It's important here. I kind of wish they would have called this middle index. It's not the middle value of the array. It's the middle index. So we're going to say if array at our middle index is equal to the value. We found it. Found is true. Our position is equal to that middle value. And then our while loop will become false the next time it runs. Otherwise, we're going to check that middle value. If array at middle is greater than value, the thing that we're looking for, set our last index to middle -1. Okay, so that's going to set the bounds for our last index now, and basically set the bounds so that we're searching only half of the array now. Otherwise, this is basically flipped. If array at middle is less than value, we're going to set the first bounds equal to middle +1. Okay? So now we've reassigned, after an iteration of this, we've reassigned either the last or the first. We're going to come back up here and we're going to search that half of the array. Or forget about the other half of the array. We're just going to focus on either the higher or lower half. Okay, we're going to find the middle point. We're going to check and see if we found what we're looking for. If not, we'll go ahead and adjust either the last index or the first index, rinse and repeat until we found what we're looking for. Or not. Maybe we don't find it. My mouse is locked. What's going on here? Hold, please. Okay, mouse died midstream. Real professional here. Okay. So if we want to search something, we don't just have to search through arrays of integers. We can search through arrays of any kind of object. And when searching an array of objects or structs, the value being searched for is a member of an object or structure, not the entire thing. So this would be like if we want to search through an array of people objects. Okay, a person object might have first name, last name, an age, favorite color, where you grew up, address, all that good stuff. When we're wanting to search through a list of people, we still have to search through a member of the structure, not the entire object. Like, we have to define what it means for one person to be greater than or less than another person. And in this case, we can just assume that that means their age. If Kevin is greater than, I don't know, Bill, that means that my age is greater than or equal to, well, greater than Bill's. You have to define that, though. You have to like set up what it means for objects to be greater than or less than. Member in the object or structure is called the key field, and then the value used in search is the search field. So again, we have the search and then the key, or needle in a haystack. Let's see what 9.3 has in store. Yeah, this is good. We can talk through this one. Searches an array of inventory objects to get the price of a particular object. Shows how to perform a linear search using an array of objects. So we have our inventory class here. We've got some private data members, item code, description, and price. We've got a public constructor here and two constructors it looks like. Here's our simpler one where we're just sort of initializing the private data members to some dummy data, some default values. Then we have a constructor where we can feed it what we want those private data members to be initialized to. Yeah, and functions to get and set, as we would expect. So get code. Yep, as we would expect here. And then we have, yeah, okay. So that's our class. Here we have just a regular function prototype. So this code listing file is getting a little bit long. Probably I would have separated the inventory class out into its own header file, but that's okay. Just keep in mind that the search function here isn't part of the inventory class itself. Let us see. And here, okay, inside of main, they're creating an array of inventory objects with a bunch of initialization here. We have the item code we're looking for, the position that it was found in, and if we want to look it up again. So we have, keep in mind, we have a list of inventory objects. We're going to enter an item code, the user is, and we're going to save that away into desired code. We're going to search for desired code in that array using the search algorithm. Let's see what that search algorithm is. That is, the rest of that main code is just like doing the looping again, and if the thing was found or not. In here, we've got a const array of inventory objects, the size, and then the thing that we're looking for. And check it out what we're doing here. This example is like almost the same as the other linear search example, only the difference is right here, this comparison. If the object at a given index dot get code. So before we just said like array at index equals value. The only difference here is that we're saying object at location index dot get code is equal to the value. The only thing that changed is how we get, like what we're comparing our value to. We didn't need get code before because we weren't using complex objects. Here we just use get code. If it's found, we'll return the position, set found as true, all the familiar suspects there. Sorting algorithms. Okay, so we just covered searching. Now we'll talk sorting. So arranging values into an order, either alphabetical, ascending, or descending. Again, tons of different sorting algorithms. And there are like best ways to do this. There's best practices for sorting a list of data. You'll learn about many of them if you go on to a four-year college or university. We're going to talk about two today. Very simple ones. Bubble sort, which is really a bad way to sort things, but it's easy to talk about, and then selection sort. It's a little better than bubble sort, but not much. So bubble sort, very easy. If we have a list of things that we're trying to sort, we're going to compare the first two elements in our list and swap them if they're out of order. We move down one element and compare the second and third elements, exchanging if necessary, continuing until the end of the array. We pass through the array again, repeating the process and exchanging as necessary. We repeat until a pass is made with no exchanges. What we're doing here is we're sort of sorting the element sorting the array in place. And if it's, I would ask you, like, what part of this sounds inefficient? Probably not the swapping, right? Like just swapping two values in an array, that doesn't sound too awfully costly. But the part that does, delay, maybe you can guess, is this part. Step 3, pass through the array again, repeating the process and exchanging as necessary. We might have to pass through this array many, many times to get it sorted in order. Let's take a look at why with a concrete example. So num list 3 contains 17, 23, 5, and 11. So we start. Compare 17 to 23. They are in order. 17 and 23 are in the correct order. We're just looking at those two values. So no exchange is needed. Then we move on. compare 23 and 5. They are out of order, so we're going to swap them. We're going to set 5 as less than swap 5 and 23. We're going to move on, comparing 23 and 11. Yes, we need to swap them because 11 is less than 23. Notice that the elements at the beginning of the array are out of order. That was just the first pass. It helped, like it definitely got more stuff in order, but the whole list still isn't in order. So we have to go through and do another pass. And I think that's what this slide is, yeah. Second pass starts with the array from pass 1. Okay, great. So we're going to compare 17 and 5. Those are out of order, so we swap them. Then we're going to move up and compare the next two. 17 and 11 are out of order, so we swap them. 17 is less than 23. No exchange is needed. That's the end of the second pass. So now things are looking pretty good. In fact, they are completely sorted. So moving on to slide 3. The third pass starts with the array from pass 2. So now we're going to compare. Is 5 less than 11? Yes. 11 less than 17. 17 is less than 23. By the time we're done looking at this array, we have made no swaps. We didn't need to because it's in order. So we didn't need to do anything. That means the array is sorted. Bubble sort trade-offs. So it's easy to understand and implement. Disadvantage, it stinks. It's very, very slow because of how many times we potentially have to pass through the array. 627 is where we'll find an implementation of bubble sort. Cool. So we've got two functions to help us out with bubble sort, and I would encourage you to code this on your own if you have the time. I will say too, by the way, that searching and sorting algorithms oftentimes show up on interview questions. So potential employers like to throw things like this at you and see if you can not necessarily code up bubble sort, like type it out in C++ in front of them, but more or less give them pseudocode for how you would come up with the solution. So not necessarily like writing out the code, but writing out an English description of how you would write up the code. So part of this bubble sort involves two functions. One is the bubble sort function itself, and then the swap function that's going to do the flipping of the values. And you can see that swap accepts two references to integers. The bubble sort function accepts the list of things that we're sorting and then an int. Let's see what that implementation looks like. Very, very short here, you can see. Okay, so size is the second int. I wasn't quite sure of what that second one is, so we're passing in the size of the array too. So we're going to have two nested loops here. When you have nested for loops, that should be a red flag warning sign that what you're doing probably isn't quite as efficient as it could be. So we're going to take max element equals the size of the array minus 1. While max element is greater than 0, subtract from it. Then we're going to do another inner loop. Int index is 0, index is less than max element, index plus plus. And here we're going to start comparing. If our array at given index is greater than array at index plus 1, we swap. And we pass those two values down to our swap function. So this is a classic swap function, very common algorithm where we create a temp variable. It's going to be equal to the value of a. We set a equal to b, and then b equals temp. Cool. So if no exchanges occur in a pass in bubble sort, then the array must be in order. This can be incorporated into the bubble sort algorithm. So basically, and that's why I looked at this a little bit puzzled, this is doing worst case bubble sort every single time. Like this is looping through our array using the maximum possible number of iterations. Very, very slow. We can improve it though. In other words, if we pass in an array that's already sorted, this thing is still going to do its thing. Going through and checking every possible combination of swaps to make sure everything is in order. However, we can detect if there was an exchange in the inner for loop and set a Boolean flag, test a flag in the outer loop, and terminate if no exchanges were made. So in this case, we would set a flag that says like, have we made any swaps? Yes or no. If by the time we get through the inner for loop and we haven't made any swaps, that means we know that the array is in order. Next type of algorithm, selection sort. So here's the English description, not even pseudocode really. We locate the smallest element in the array and exchange it with the element in position 0. Then we locate the next smallest element and exchange it with the element in position 1. Continue until all the elements are in order. Sample run of selection sort. So here we have an array called numList that has the following values: 11, 2, 29, and 3. Smallest element is 2, which we have to kind of keep track of that, right? Like there's nothing magic that we can ask our array to tell us what the smallest value is. So somehow we have to keep track that the smallest element is 2. But the algorithm goes that we find the smallest element and we exchange it with the element at subscript 0. So we're swapping 2 with 11 because that is subscript 0, the 0 index. The element in position 0 now is in order. So we're sort of like creating sections of the beginning of the array that we're guaranteeing are in order. In this case, the pieces in red are going to be the parts of the array that are in order. The next smallest element is 3. So exchange 3 with the element at subscript 1. So the element in position 1 is now in order. So 2 and 3 are in order. Then we look at the next smallest element, which is 11. And I should point out that it's the next smallest element of the unsorted elements. That would, of course, be 11. We swap it with subscript 2, and now, yay, we're in order. I'll leave the code for you to check out on your own on page 632. Take a gander at that. Probably even type it out, I would recommend. Considerations for sorting. So it doesn't, how should I say? Yeah, it doesn't have the bubble sort's ability to terminate the sort when it detects all the elements in order. Selection sort is more efficient than bubble sort. So let me rephrase that. Best case bubble sort is better than average case selection sort. Because with selection sort, we don't really have a way to terminate it early if everything is in order, due to the fewer number of exchanges that occur in selection sort. Again, we oftentimes talk about worst case scenarios. Computer scientists are very pessimistic. We want guarantees about how slow could this code possibly run? What is the slowest possible speed at which this code could run? Sorting an array of objects. So just like searching, arrays can be sorted if they contain objects or structures. The key field determines how the structure or object will be ordered. When exchanging the contents of the array, the entire structure or object must be exchanged, not just the fields. So if I'm sorting an array of people, say I want to sort it by age. So the field that I'm sorting on isn't my first name, my last name. It is the age field. It's an integer. What that means is that Kevin, age, oh good grief, 38, I think. When I compare that person object with Bill, whose age, I don't know, 40, I don't want to swap just the age field. I want to swap the entire object so that Bill's age doesn't change and my age doesn't change. Let's take a look at 634 together. Uses the enhanced bubble sort algorithm. Oh, yeah, that's a little out of order. Let's just take a look at what changed here. Got a nice little display inventory helper function. Yeah, right here. It has a swap like we would expect, but here the bubble sort function accepts an array of inventory objects and the size, of course. So here's the change. We're keeping this little Boolean up here that is checking to see if we've made a swap. So if we've made a swap, we're going to keep going. And any of the pass-throughs through the array, if we've swapped two elements, we're going to mark it as true, and that means we need to go ahead and make another pass-through. If we make it through and haven't made any swaps, then we can assume it's in order and we end bubble sort. Again, it could be the case that the array we pass in is in order, in which case we're only going to make one pass through it and just be done. There's no more work to do. We're trying to make bubble sort a little bit smarter. Sorting algorithms can be applied to vectors as well as arrays. So just slight modifications to sorting functions to use vectors in the type of the function. No need to indicate the vector size as functions because we can use the size member function. So page 637. All right, so because we're using vector, we're using STL, we have to include vector. And what has changed? So what has changed is the function prototype signatures. So we have selection sort and binary search. When we pass in our vectors, we're passing in a reference to a vector of strings. And here we have binary search, again, passing in a constant reference to a vector of strings. Yes, that's a lot. That's a mouthful. A constant reference to a vector of strings. That's our haystack, and then the needle that we're searching for is some string. What does that look like down here? Well, there's not much difference. Notice again how we don't have to pass in a size. We can just say v.size, so our vector array dot size minus 1. Really, that's the only difference. Anytime we saw the size variable in the other examples, we're just substituting v dot size here. It's nice. Vector is a little bit smarter than our array, so we can use what they have for us. Now the juicy stuff. So introduction to analysis of algorithms. So we've seen two searching algorithms. We've seen two sorting algorithms. What makes one better than the other? We've tried to talk about, like at a high level in English, why one is better than the other. But is there like a concrete way that we can sort of prove that? Well, there definitely is. We can measure the efficiency of an algorithm by the space. So how much computer memory needs to be used to execute the algorithm, and then time, how long it takes to execute it. And I would argue that these days, now that hard drive space is becoming cheaper and cheaper, space isn't really that much of a consideration. It is a consideration, like we don't have infinite space or infinite memory to use, but it's not as important of a consideration as the algorithm's time. People want fast code. They want their apps and websites to run really, really fast. They probably don't care as much behind the scenes how much memory you're using. That may be an overstatement, but generally speaking, time is more important than space. So analysis of algorithms is a more effective way to find efficiency than by using empirical data. So we could, like, if we wanted to see how selection sort compared to bubble sort, we could feed both of those things, both of those functions, an array with 1 million elements and just basically start and stop a timer and see which one took longer and by how much. By doing that over and over again with different input sizes, we could maybe even like chart it. So given an input, an array of size 1 million, selection sort took this long to finish. Given an input size of, 500,000, it took this long. And then measure the same way with the other sort. And then compare the graphs. What this is saying is by doing an algorithm analysis, we don't need to run those sample cases. So terminology. Computational problem is a problem solved by an algorithm. An instance of the problem is a specific problem that is solved. The size of the instance is the amount of memory needed to hold the data for the problem. So basic step, what does that mean? When we talk about like how fast algorithms run, we sometimes talk about how many steps do they have to take. Loosely speaking, that corresponds to sort of how many lines of code need to execute when the thing runs. And so we call that the basic step, an operation in the algorithm that executes in a constant amount of time. What is an example of this? I don't know. Adding 1 to a number, an assignment statement. What else? Getting the size of our vector, accessing an element of an array. Those are all basic steps. It's like 1 unit of work almost. Oh, there are some examples here. Exchanging the contents of 2 variables, comparing 2 values. A non-example of a basic step, finding the largest element. And I would probably even say swapping. Like swapping is a function that does, I would say, 3 basic steps. Yes, okay, so the complexity of an algorithm is the number of basic steps required to execute the algorithm for an input of size n, where n equals the number of input values, in other words, the size of the array. We talk about the worst case complexity of an algorithm, the number of basic steps for input of size n that requires the most work. So that's worth stating again, that requires the most work. Again, we're pessimists. We care about the worst case complexity. We care about the steps that do the most work. We don't care about how fast something could run under ideal conditions. We care about having a guarantee that this thing could run no slower than this or that. There is an average case complexity for a typical average inputs of size n. That's a little bit more like in order of, I guess, relevance or importance. The worst case is the most important, average case is the next most important, and then best case is not very important. Here's a good example of some basic steps. Find the largest value in an array of size n, where A is our array. So we're going to do some initialization here. We're going to say some variable called biggest is equal to whatever value as at the 0 index of our array. We're going to set our index to 0. While index is less than the size of the array, do stuff. If array at location n is greater than our current biggest, then biggest equals whatever it is. End if and while. This is pseudocode if you didn't know. So lines 1 and 2 execute once. So there's like one tick, here's another tick. Test in line 3 executes n times. Worst case. In fact, always case, I guess. We're not really breaking out of this early if we happen to know that we found the largest element, because we don't know. We have to really process each element of the array. So the test in line 3 executes n times, where n is the size of the array. The test in line 4 executes n times. Line 6 executes n times. Due to lines 3 and 4, the algorithm requires execution time proportional to n. So again, because of lines 3 and 4, here and here, this algorithm requires execution time proportional to n. So as n increases, the time will also increase proportionally, or we can say linearly. And that would look like this. This is something I added because I like this chart. I found it helpful for doing things like preparing for interviews, but I said linearly. So like this line that cuts basically this square in half, or this rectangle in half. Oh, it's also down here. O of n, specifically, that's what we're talking about. So this line, or f of x, if you want to use math terms. Comparing, complexity of algorithms. So given two algorithms, f and g, with complexity functions, f of n and g of n, for input of size n. This isn't going to make much sense to you. I would, again, rather draw your attention to this chart. This chart is basically a visual of what it's trying to explain in this slide. Check it out. So as we kind of go counterclockwise on this little graph, we're getting less and less efficient. We just talked about n, basically proportional. That's a pretty good speed. Like there's many other speeds that are way worse than O of n, but there are also some that are better. There's O of log n, O of 1, which is just a constant. O of n is still in the green. N log n kind of in the yellow, and then some really bad ones up here in the red. O of factorial is like bad, no. Okay, so that all this is saying is that certain things are faster than others. Certain run times are better than others. And I said it, but it's worth having a slide on it. Big O notation. F of n is big O of g of n if f is big O of g for some mathematical function, if that ratio approaches a positive constant as n gets large. I'm going to show you a better graphic that basically is illustrating what this is. Faster rate of growth and less efficient algorithms. Let me find that picture. Here we go. Let's grab it here. In the files section of Canvas, I have uploaded a cheat sheet, algorithm analysis quick summary. This is something I actually created for myself to help me in college, and it's still relevant today. So I've given it to you free of charge as a PDF. Hopefully. Let's download it. Here we go. So all that big O notation slide was trying to get across is this. So say our say our algorithm is represented by this line. So that's f of n. Say that's our, I don't know, magic sort algorithm that we just came up with. Our magic sort algorithm runs in this kind of line. This kind of curve, I'll say. So if C of G of n is big O of f of n, it looks like this. For every number of inputs we give to some function, it's always going to be greater than the same input for our sorting function. Feel free to read through this PDF. I kind of break it down a little bit better than what the book is trying to show us here, but hopefully you get the idea. So there's some function that bounds above our custom sorting function. So big omega basically is the opposite of that. So there's some function that bounds below our whatever function, our algorithm, our custom magic sort algorithm. And then theta, this is like your average case. So there's some function above and some function below that constrain or create a bounds for the runtime of our magic sort algorithm. Check it out, especially if you're, like, even if you don't use it a ton this semester in our C++ class, I think that you'll appreciate having something like this around when you go to university and even when you go and apply for jobs. I use it. You should too. Okay. Yeah, just explaining where to find that. If you're on YouTube watching this, post a comment on the video and I'll send it to you for free. There's more stuff on Canvas if you want to get into more on algorithm analysis. There's even like a multiple page PDF that breaks down the analysis of algorithms even more. Again, if you're on YouTube, let me know. I'll share it with you for free. Or, hey, if you just want to talk about this stuff in email and go back and forth on algorithmic complexity, I'm happy to do that too. There is a little assignment that I will just pull up. Chapter 9. 4 little problems, mostly asking you to utilize the sorts that we just talked about, just with some hard-coded data and then reading it into a list. This is the first lecture we've completed that's less than 1 hour long. Go us. We're moving up in the world. That's not going to last for long, though. Next chapter, chapter 10, I believe, yes, is all about pointers. So we can treat chapter 9 as kind of a nice break before we get to the stuff that tends to turn a lot of people away from C++. It's why C++, one of the reasons why it has a bad reputation. In fact, I know some of you have mentioned that you stopped learning this language on your own when you got to the pointers stuff. So we'll try to break it down as best we can and make sure that you understand not only how to use pointers, because they're not terribly difficult to use from a syntax perspective, but why? Why do we want to use pointers? When I first started learning them, I didn't have a clue why they were important. It seemed like I could do everything I wanted to do without them. So why do we need to learn about them? So all that and more in chapter 10 next time. Until then, I'll say thank you very much. See you next time.